So, hi everyone. Today I would like to welcome you to the third presentation in the P4 Expert Roundtable series. My name is Mohammed Shahbaz. I'm a postdoc at Stanford University and the moderator for this talk today. It is my pleasure to have Itzik, Ashkenazi, and Matty, Kadosh in today's roundtable session. They're going to talk to us about their work on enabling PBT-on-Demand using Mellanox P4-Capable hybrid switches. So I will now hand over to Itzik and Matty to introduce themselves and talk about their great work. So off to you, Itzik.
Hi, nice to have you to come and meet with you. My name is Itzik Ashkenazi. I'm the chief engineer of the networking lab in the CS faculty in the Technion. In the lab, we conduct research projects as well as projects with the industry, networking projects with the industry, mainly for undergraduate students.
Hi, my name is Matty Kadosh. I'm from Mellanox Technology. I'm a software architect at the Switch Software Architecture Group, especially looking at programmability, switch programmability in specific programming language, and so.
Okay. Okay, so should we share the screen now?
Yeah, please go ahead.
Okay. I'll share my screen. Okay.
Cool, we can see that, yeah.
Okay, so we will discuss today about the project. We called it PBT-on-Demand on Mellanox P4-Capable hybrid switch. The agenda of this presentation will be, we will shortly introduce the people that were involved in this project. We'll talk briefly about enhanced networking network monitoring. We'll describe briefly the idea behind PBT-on-Demand. And we'll talk about the Mellanox switch, which we actually implemented the PBT-on-Demand on this switch. And we will finalize with a demonstration of a POC implementation we did lately in the lab. So again, this project is a joint project between my lab, the networking lab in the Technion, and with Mellanox. With Mellanox, we work already between 3 to 4 years, and we conduct various projects around mainly about around programmable switches. So we collaborate with them very nice. The students that implemented this project, it was in last semester. Their names is Sami and Abdallah. And the instructors were Alan and Matty from Mellanox and myself. So, enhanced network monitoring, why we need it today? We need it because for various needs, we are using it for better traffic engineering. We use it for security to detect DDoS attacks. We need it for detection of anomaly in the network. And the most important thing, we need online troubleshooting, online and fast troubleshooting on what is happening in our network. Currently, we have the OEM protocols, which we all know they are working. They are in most switches. Maybe today they are even implemented and deployed. .1ag is CFM, or Y1731, which is called also SAA. They are good, they are useful, but they have a major disadvantages. Among them that they are working in the control plane. They produce, you need to produce synthetic traffic, and they also overload the CPU, the CPU of the switch. So they really cannot help us to fast detect and troubleshoot fast, let's say online, our problems in the network, and they don't give us good network visibility, fast and good network visibility. We have the net flow, which gives us good flow statistics, but still it's not enough because you can't see at the packet level. We need, in order to troubleshoot, we need the real packet information. So we can do mirroring, but mirroring is, to mirror all the packets is really not a good option because it will overload the switches, and of course it will overload the data path. So we can do mirror. We can mirror sample packets. It's a good idea not to mirror all the packets, mirror only samples. And actually, we also introduced 2 years ago a sampling on demand framework, which take into account that the mirroring and sampling is an expensive resource. And this framework was proposed by the professor of my lab, Professor Reuven Cohen. And it talks about ability to optimize the sampling resources in the switches. The controller will have the sampling management module. He will decide which switch will sample what flow according to its capabilities. In each switch will be embedded sampling module, which will do the sampling and will send it to the collector. Will send the packets, the mirrored sampled packets to the collector. And the collector server will analyze the packets and the sample packets and will give us good online visibility about the switches. So this framework we felt that it's a good framework to base on it and to take it one step forward. And here we introduce the PBT-on-Demand. Postcard PBT, which stands for postcard-based telemetry, actually uses the framework or the the basics of the sampling on demand, and export with the packet, with the sample packet, additional online metadata information like the switch ID where the packet has just traversed, timestamps of the ingress and the egress of the packet, the latency, how much time it took the packet to pass through the switch. And very important, it can give us also ingress, egress queue occupancy. That means it gives you inside visibility on what is going inside the switch. PBT-on-Demand, again, since it's based on it will be based on the framework of sampling on demand. It will give the network controller ability to tell each network switch which PBT what sampling rate he will perform according to the switch capabilities, and this to be in the most optimal way. So up to now, what we say is that we have the sampling on demand, which is, this is the basic of PBT on demand. which takes the basics of sampling on demand and gives us more visibility to the switches. For this implementation, we collaborated with Mellanox and worked with their switch, which is P4-Capable. Among its very impressive features, since it is based on the Mellanox Spectrum 2 silicon, it is actually hybrid packet forwarding silicon or switch. It has concurrently legacy capabilities and programmable capabilities. Briefly, we will describe here the Spectrum or Spectrum 2 P4 target architecture. It has actually, it is based on since it's hybrid, it has both the legacy functionality, which we see in the gray blocks, which those blocks cannot be changed out of the box, and when the user gets the switch, he gets out of the box those functionalities working as today the legacy features. In addition, it has programmable blocks that the user can program, enables the user to program the pipeline, and this what does the switch, gives it to be why we call it hybrid functionality. So it has the parser block that the user can actually add here few more new headers that belongs to new protocols. You can program the match and action tables on the ingress of the port before the bridging, before the switching. You can do manipulation before the routing, and also you can use various actions like mirror packets, packet modification, packet tunneling, etc. You can match, you can program after the routing the match and action tables, and you can program the egress on the egress. You can program match and action tables, and you can do various actions like egress mirroring, packet modification, etc. Actually, when we implemented the PBT-on-Demand, we actually sat here, and all the manipulation and the new actions were done in this block of the egress port. This is another look of the hybrid programmability. The user is writing the P4 program. In our case, we wrote the telemetry PBT P4 program. We compiled it with the P4 compiler that we received from Mellanox, and actually deployed it here in this block. We deployed the P4 program, sorry, and also implemented the telemetry application that can enable you to program the tables that we programmed in the P4 program. The Mellanox has in their P4 implementation few extensions that enables them enables the user to extend the P4 in order to provide the functionality that you want. Among them, they have the policy-based switching. They have ability to trap packet and send it to the CPU. they have the ability to mirror packet and to a remote controller or remote collector, like we did using GRE. Actually, in PBT-on-Demand, we use this this extension, the mirror to remote L3. Also, you can define, you can have set polycell. All those primitives are embedded in the P4 code, and you can use them with the standard actions. In addition, the Spectrum 2 gives you ability to the ability to add metadata that is added to the packet, so you can add it. You can add this metadata and attach it. In our case, in the PBT-on-Demand, we took we were able to use the metadata and tunnel it via GRE to the remote collector. For the PBT implementation, we used the Spectrum 2 Telemetry Header implementation, which is added to the GRE header. And here, actually, you can see the ingress buffer occupancy of this is the ingress buffer occupancy of the packet that we just sampled. We can see exactly what was the ingress buffer occupancy when he entered the switch. What is the egress buffer? That means when the packet was switched or routed to the egress port, we can see, and it reached the egress queue, you can see the egress buffer occupancy as well as the latency inside the switch. So we use this special header in our implementation. In our POC, actually our POC was very simple. We used two Mellanox switches. One is the Mellanox SN3700 with Spectrum 2 silicon, and another Mellanox which is a switch which is Spectrum 1. Here only we use this switch for the packet switching. What we have here is a traffic generator with DPDK, which was generating high rate traffic to the Mellanox switch. The traffic in general is switched to the egress port and to the next switch. And what we added here, we implemented and programmed. We implemented here and programmed the P4 program, compiled it, and activated in the Mellanox switch a Docker image, where we run, where actually the P4 program is running and enables you to via this Docker to program the P4 tables. So the traffic generator was generating traffic, and once the P4 program was deployed, it started to mirror sampled traffic according to the sampling rate that we programmed to the switch. And it was sampling the traffic with the postcard telemetry that we added and send it to the collector. Once we started on the traffic generator congestion traffic, we could now get in the collector all the data that we needed in order to identify and troubleshoot what is causing the connection. or let's say at least the root cause of the connection, of the congestion, sorry. Okay, so here we have a short video of the demos, what we did. I will start it. We will first show how we program the P4 table entry via the P4 runtime Docker. Here we program the sampling rate. In this case, the sampling rate is 1 to 32. And we program here to what port to mirror the traffic, the sample traffic. And we started the traffic generator. Traffic generator was sending traffic between 1 gig to 10 gig. And you can see in the collector, we implemented a nice GUI that shows you online the latency on the switch and the egress buffer occupancy. So you can see that we have a window of 5 seconds that can show you in 5 seconds, you can see the latency and the buffer occupancy. Another feature that we wanted the students to do is to try to detect the heavy hitters, because they get, in the postcard, they get the 5 tuples. So we asked them to identify which flow, let's say, is the heavy hitter, or the top 3 heavy hitters. So they show you online by analyzing the postcards, the received postcards, the heavy hitters. So actually what we saw here, we can see clearly the egress buffer occupancy that we got using the postcards. For example, here you can see that once there is a congestion, the egress buffer occupancy is rising here because of the congestion, and also the latency is rising up once you congest the switch. And here again you can see the heavy hitters, the top 3 heavy hitters that to be identified in that traffic. Okay, this is it.
Okay, so cool. Thank you so much for the nice talk. So this is very interesting work. So I think one question that pops up in the mind is, you talked about sampling on demand, and then you said you used it as a baseline for your PBT on demand work. So can you elaborate a bit, like what was the main difference between sampling on demand and PBT on demand?
Yeah, sure. While sampling on demand was sending only the packet or a fraction of the packet to the collector. So in the collector, actually, you could identify only let's say, you can analyze the flows and do flow statistics, etc. Here we added, actually, in the PBT on demand, we added more telemetry, more information about this specific sample packet. The egress queues, ingress queues, latency, timestamps. So it gives us more capabilities to troubleshoot the problem.
Okay, okay, cool. Yeah. All right. So, but in that case, it seems like you are extending the amount of state that you can send to the controller by encoding it on top of the packet. But the question is, like, how is it then different from this, like, sort of the INT version that is out there that came out with the P4 organization, like in-band network telemetry? Because they do allow you to do the same thing, that you can encode like internal information of the switch on the packet and send it out to maybe some destination, a collector, or something else.
Yeah, it's right. Both PBT and the PBT on demand or INT, both are end-to-end debug, let's say, debugging tool or framework that you can use in order to debug end-to-end what is going on and troubleshoot it. The main difference that I see is is one problem with the int is that it causes the packet. The packet is growing from switch to switch. So if your path needs to traverse a few 10 or 20 switches, so your packet is can overlap with the extra information that you supply. So here we don't have this problem. Another case is that actually we can in the PBT on demand we can manage the rate, how frequently you do the sampling, and so we can play with it. We can zoom in once there is a problem. We can make the sampling much higher. We have in this case we gave a little bit more mechanism to I think to control and troubleshoot your problem faster.
Okay, that's very interesting to know. Okay, so but I think the other thing that when I was looking at the INT work is like they talked about like being able to capture like these very small fine-grained nanosecond time scale bursts. But in your case, when you're doing say PBT-based sampling, say at sort of not like on a nanosecond time scale, but at like multiple second time scale, is it still possible to get that fine-grained level detail, or will you be able to miss these microbursts that come in the network using your PBT-on-Demand implementation?
Let's say we have the framework, so we can, according to the traffic, we can embed more logic in the manager, in the controller that will be able to customize the sampling rate. And once he starts to detect something that is anomaly based, let's say on machine learning or something like this, he can configure, the controller can configure to higher the rate and customize the rate accordingly. So I think the framework that we suggest here gives you more, let's say, customizing abilities versus.
Okay, cool. All right, so I think let's move on to the other cool part of this thing. So you use these Mellanox P4-Capable switches, but as I understand, they are like, you're calling them hybrid switches. So I would like to understand what is the difference between like the Mellanox hybrid switch and the P4 teaser switch, for example, that we have out there. So what is the main difference between a hybrid and a fully programmable switch?
Matty.
In your case.
So the main difference between an hybrid programmable switch and a fully programmable, and maybe calling it hybrid and fully programmable means it sounds like hybrid switch has kind of less programmable capabilities, but this is actually not accurate. So the idea behind hybrid programmable, which actually totally supported by P4-16 language, is the fact that you have multiple programming points into the silicon, and in between you may have a given logic. The power of that is that you can program only what you need. So as a vanilla switch, and this is one of the this is the most powerful aspect of it, is that you can take a switch with the NOS fully working. So you don't need to configure the routing. You don't need to configure. You don't need to handle all of it. If the only functionality that you want to add is something on demand, that this is the only thing that you need to write. You don't need to write FTP, and you don't need to write routing, but it does not mean that you cannot. So every programmable piece within this pipeline can actually replace the whole pipeline. So you can take the first programmable block and say, okay, I want this block to handle all of it, do encapsulation, do routing, and off you go to the port. But this is up to you. On the other end, you can say, I want this block only to replace overlay. I want this block only to do something on demand or other aspect. So it's program on demand, only what you need and not what is already out there.
Okay. So maybe the next question is like, doesn't this like sort of bloat the size of the switch? Like, for example, you have both the fixed functionality in the switch as well as the programmable functionality that can still do what is fixed function in that switch. Why not just have the programmable one? Like, is there a specific need or a reason that you think it has to be there? Maybe like because the existing fixed function logic is well tested, so that's why you want to go with it. So what is the reason for having like both? Yeah. Go ahead.
First is we don't want to invent the wheel. So if the wheel is already invented, like it's called routing or bridging, let's use it if we can.
Okay.
On the other aspect, actually, we do have an optimization. So if you know that your hardware is going to do FDB, you can optimize your lookup to an FDB. So we did it. So we assume that FDB is most likely to be there, and we assume that routing will most likely to be there. Again, we are not forcing that, but we assume that in a lot of cases, we will have routing and we will have bridging. So we can use a dedicated hardware or dedicated key that can do that in the most efficient way. But in addition to that, feel free to define your own action, your own chain, your own parser, and program the switch.
Okay, cool. Okay, so the thing is like, I think the other thing that people would be interested in knowing is like, what features and what extensions did you add to the language, or maybe to the underlying architecture to enable PBT? Like, how did you expose that feature to the user, like in the P4 language? Was there a new architecture that you had to build, or was there a new extern function or new extensions that you added, and how you can use them? Are they still being used in the match action table, or do you use them maybe in the deparser stage or some other place in the switch?
So it is used as part of the action, and yes, the architecture, the target architecture that the student work on was Spectrum target architecture. It wasn't a PSA or a V1 model. It was a Spectrum target architecture, and as such, we exposed some additional actions, and some of them was related to sampling on demand and post on demand as well.
Okay. So do you have any idea, like if we want to sort of implement this PBT on demand architecture on, say, the PSA architecture, is there anything new that we need from the Spectrum architecture to extend the generic PSA architecture we have, or it can be implemented as is on the sort of the PISA architecture that they are developing, like the specification we have for the portable switch architecture?
I would say probably you can easily implement it on the portable switcher. You may need to have an action that will do the metadata inside, like defining the format of the metadata. One in that kind of like a specific format that you would like to get in your postcard. But other than that, I think that everything can work on the PSA architecture as well.
Okay, cool. Okay, so this is amazing. So I think when you were talking about this sort of like this PBT on demand architecture, the way the switch implemented it, like it encodes these bytes on the packet over a GRE tunnel and send it out to the controller. So one question is like, what if I want to encode something new mission that comes up in a switch? Do I need to recompile the sort of the whole P4 program, or is there a dynamic extension that I can say, oh, instead of ingress and egress buffer, I want to say in like find out the number of drops that are happening on a particular port or something?
So an additional, I think, cool aspect of the hybrid programmable switch is the fact that we can do everything. Okay, I would say almost everything in runtime. So you can change the parser in runtime. You can apply a new match action or a new chain of match action on runtime, and you can change the postcard, the content in runtime as well.
Okay, cool. So I think as a last question, what is the key use case for PBT in your mind? Like, what is the sort of the poster child use case that you think PBT can actually help with?
Here I would like to, let's say, to present a slide. I will share my screen again.
Sure.
Okay, so this is a use case that actually I received from Mellanox. I think they are about to offer it also to their customers, and also we are going in one of the next student projects that we are now working together. We will implement part of it. So what we have here, the user that is sending traffic along those switches to the other side. What Mellanox want to do is to use the PBT-on-Demand framework that we just demonstrated, and implement the PBT-on-Demand P4 program in all the three switches. So what will happen here? Here, the use case is a little bit more advanced. The use case will start sending to the collector the postcard telemetry only on some trigger. That means if the threshold of the egress buffer passed cross some threshold, predefined threshold, only then start to find. So here there's an additional work that we still need to do in order to implement it, because we are doing the sampling not based on trigger, but once the user configured the sampling. So, but the fundamental is of PBT-on-Demand is exactly here. So what will happen here upon trigger? The agent will send postcard telemetry, exactly what we saw, to the collector, and in addition, will mark the packet. Let's say the DSCP, one of the DSCP fields will mark the packet and send it to, and will forward it to the next switch according to the regular forwarding or routing decisions. Here, this switch will have a P4 program that will, not upon trigger, but upon a match of the DSCP marking, he will send telemetry data, postcard telemetry data to the collector. Same to all the switches on the path until the last one that will send telemetry and will of course remove the marking. So this is a use case that can use the building blocks that we demonstrated in the PBT-on-Demand, and we'll take it, let's say, one step forward and give it. And I think, Matty, this is something that you are going to propose it to your customers, right?
Right. And actually, this answers the question that Muhammad asked before about can we detect microbursts? So this is actually how can we easily and very efficiently detect microbursts? Like if one queue was exceed the threshold, then we start monitoring that flow and providing to the user. This is a flow that suffer from latency or buffering and so on, and we can actually provide a path, the full path, the latency per hop, the total latency, queuing per hop, and so on. And it will be, it can provide a meaningful information for a user to identify and find bottleneck in the network.
Okay, awesome, awesome. So I think with that, let us thank our speakers for such a great discussion. I hope everyone enjoyed it. Thank you all for joining in. And with that, we conclude our session. Stay safe, everyone. Bye.
Thank you very much. Bye.